So, it is quite difficult to quantify this liquid hold up, especially at this high temperature. So, people have done the experiment again in the cold condition, the way that now we saw in this previous video. In the same way, people have done the experiments to quantify liquid hold up static and dynamic using the room temperature experiment. So, one of the researcher known as Fukutek and his team, they did extensive experiments to find out the liquid hold up in various conditions, and some of them resembling to the blast furnace. So, many types of liquid of different properties and packing they had used, and finally they come up with these two correlation. So, Hs is the static hold up of the liquid is equal to this. So, remember this liquid hold up which we are discussing in absence of gas flow. As I mentioned previously, when gas flow is not there, still there is a liquid sitting in between the particle. So, this is in absence of gas flow, the static hold up is represented by this correlation, where rho L is the liquid density, g is your acceleration due to gravity, phi s is the shape factor, dp is the particle size, sigma t is the surface tension, and theta is the contact angle between liquid and solid, and epsilon is the void fraction in the packing. And similarly, the dynamic hold up given by them is represented by this equation. Again the same symbols are used. Here VL is the liquid velocity, mu L is the liquid viscosity, and all other terms we have already defined above. So, using this correlation, one can get some idea about the liquid total liquid hold up. Once you add these two, static and dynamic, so you can know the total liquid hold up, and you can modify your void fraction of the packed bed, and then you can calculate the gas velocity and liquid velocity, because that is the one which is important in calculation of heat and mass transfer, and those are the one which are going to get affected by these two parameter, and that is why they are very important. So, these equation as such as I said was developed under cold condition, but they can be used for liquid metal and slag. Now, this is in absence of gas flow, but once we start the gas, situation changes, as you have seen in the previous video. When the gas flow starts, how the liquid get displaced, and not only get displaced, even the more static hold up, it is sitting just in between the void. But the way Fukutek et al. Have developed this correlation, they do not have the side injection, they had the bottom injection. So, where you do not see that sort of phenomena, still in absence of any other acceptable correlation, one can use this correlation for blast furnace till the further development takes place in this direction. So, the liquid hold up in absence of in absence of gas flow still, now the meter which you are observing in dynamic hold up, these 4 actually they are nothing like a Reynolds number, Galileo number. So, first one is a Reynolds number, second one is Galileo number, third one is capillary number, and the fourth one actually we call dimensionless interfacial force. So, this is your this one. So, Reynolds number, Galileo number, capillary number, and dimensionless inertial force number. So, if you represent in the non dimensional number which are quite well known, then the equation you can write in those terms. So, static hold up is a function of capillary and interfacial force, inverse of that, and the dynamic hold up is a function of Reynolds number, capillary number, interfacial force, and inversely Galileo number. And once you know these, you can calculate the total hold up. And in presence of gas flow, they proposed this correlation where HT is the total liquid hold up, which is nothing a combination of static and dynamic hold up, but in presence of gas flow. ST naught is again the total hold up, but in absence of gas flow. So, this is a total hold up in absence of gas flow. This is a total hold up in presence of gas flow. So, in presence of gas flow, total hold up is in absence of gas flow total hold up plus this quantity, where xp is nothing again a pressure drop which is in the irrigated condition or wetting condition when the liquid flow is there, the pressure drop under those conditions, and with this number which are nothing like capillary number and interfacial force. So, in terms of capillary number and interfacial force number, this xp is represented in this form. HT naught is the total liquid hold up in absence of air, and delta Pw is the pressure loss in the wet when it is irrigated by liquid or in the wetting current when liquid flow is there. So, naturally one has to know then this, and for dry wet you already know about it using the Argon equation. We have used this one in many of the application previously. So, for dry bed you can calculate the pressure drop per unit length using this Argon equation, where coefficient are used 150 and this, and this coefficient depends on particle form and the packing condition. However, in terms of the liquid flow condition, the pressure drop is again given by the same equation, but in little modified way. When we say little modified way, because in the dry condition the void fraction is the same everywhere, but when the liquid is flowing, void fraction is reduced because the liquid is occupying some of the space in the packing. So, that has to be taken into care. So, essentially what you are doing, you are adding that part of the liquid as a total hold up wherever the void fraction term is coming. Otherwise, there is no other difference, and that takes care of the pressure drop when the liquid is flowing in that. And the D is defined as using this equivalent formula according to them. So, D is defined this way, and where dl actually is the virtual diameter of a liquid drop given by this formula. So, you can easily once you know that these properties are known to you, you can calculate it. So, K1 and K2 in the wetting condition, liquid flow condition, this K1 and K2, while dry condition it is there in this one. They are were estimated at 140 and 1.7 respectively. And this is if you are having a single liquid flow, but as you know in the blast furnace you have two types of liquid, one the liquid iron and another is the liquid slag. So, if you have a two liquid phases, then ST is replaced by the STS. So, total hold up for slag, total hold up for metal, and D is defined in terms of same way as we did above, but we include the another liquid here and then DL also in the same way. Then one can calculate the pressure drop. So, now I think after going through this, probably it is the time we should concentrate on some application part or some example. So, you can get an idea how to calculate and what is the importance of this liquid holdups. So, here is one example. Calculate the total liquid metal holdup in the lower part of the blast furnace, assuming there is no gas flow. So, that we are remember we are doing in absence of gas flow. Data given: liquid metal density 6800 kg per meter cube, surface tension 1.1 Newton per meter, shape factor 0.65, bed void is 0.43. These are all usually the actual conditions of the blast furnace. Coke size and in the dropping zone it is about 30 millimeter. Liquid metal contact angle with coke about 90 degree. So, that is sort of we are at the boundary of non-wetting thing. Condition: liquid metal viscosity is 5 into 10 to the power minus 3 Pascal second, and liquid metal superficial velocity, which is superficial velocity is 0.1 millimeter per second. So, you have to calculate the total liquid metal holdup. So, when we say total liquid metal holdup, so you have to calculate the static liquid holdup and the dynamic liquid holdup in this condition. And in absence of gas flow, as we know, the formula for that are these, with the static holdup and dynamic holdup in absence of gas flow. We can use these and most of the quantities are known. So, let us do that. So, using that holdup correlation, so what we have to do? We have to calculate Reynolds number, Galileo number, capillary number, interfacial force. So, Reynolds number in the packed weight is given by this shape factor. So, density is given, superficial velocity is given 0.1, particle size is given 30. So, and the shape factor is also given 0.65, void fraction 0.43, and this is 5 into 10 to the power minus 3. So, the Reynolds number of the liquid is of the order of 4.65, which is quite low. And so, under sort of a laminar regime seems. And Galileo number, again Royal gravitation force 9.81, particle diameter, shape factor, void fraction and viscosity, that gives you the Galileo number of 7.2 into 10 to the power 8. And capillary number, similarly you get by substituting all these quantity which are already given, you get 70.98. and interfacial force is about 1. So, once you know all these non-dimensional quantity, now you can substitute them into the correlation. So, for static hold up you put that, so you get about 0.0255 meter cube per meter cube. Remember this unit with respect to the packing volume, and dynamic hold up you get 1.2 into 10 to the power minus 3. So, if you look at this, you can see the dynamic hold up mostly usually in these conditions in the blast furnace, they are one order magnitude lower than your static hold up of the liquid. So, static hold up of the liquid, that is the liquid which is in between the particle and by capillary force, this it's quite a lot than your the dynamic hold up which is flowing through the void spaces. So, therefore, the total hold up would be addition of static hold up which is 0.0255 and the dynamic hold up 0.00124, that gives you 0.0267 meter cube per meter cube. So, this is your total hold up of liquid in the blast furnace, and this would be constituting almost 5% void fraction. It would be occupying the space, and even a 5% space when it is reduced is going to change your gas velocity and other parameter substantially, and that is why this importance of this liquid hold up. Now, this is actually, remember, in absence of gas flow. Now, let us do the same example in presence of gas flow. What happens? So, this is the second example which is more talking about liquid flow in presence of gas flow. So, considering the previous example, calculate the total liquid hold up in the presence of gas air when the blast volume is 7000 meter cube per minute. The value of Argon constants K1 and K2 can be approximated as 190 and 1.7 respectively. The effective diameter of liquid drop may be taken as 2 millimeter. So, already the TL is given here. So, use Sutherland's relation to find the gas viscosity. This is an important, if you have read in your undergraduate heat or momentum transfer, you would be quite familiar with this Sutherland relation by which you can calculate the gas viscosity. Who do not know that, they may use the gas viscosity as 5.4 into 10 to the power minus 5 Pascal second. The average diameter of the valley in both regions may be taken as 12 meter. Gas composition may be considered as 40% CO and 60% nitrogen, which is a typical sort of composition in the dropping zone. Temperature may be taken as 1400 degrees Celsius. In the wet pressure drop equation, consider HT equal to HT naught. So, this is a simplification. To simplify this equation, as you will observe here, this HT term is coming in the pressure drop term. And if you look at your total Holdup equation, this pressure drop term constitutes the part of x p, which is coming here. So, the total Holdup term is coming both the side, which creates a problem, means the equation has to be solved numerically with trial and error to find out the total Holdup. And due to that reason, especially for this example, for the dry bed, for the wet bed for this pressure drop, this H T which is appearing here, it is saying it can be taken as the total Holdup of liquid in absence of air, and then you can easily solve the total Holdup. So, let us see how do we go with it. Now, you need also the gas velocity, which is not given, but the volume is given. So, you can probably with this volume and with this diameter, you may be able to calculate the superficial gas velocity. So, let us see. So, here in presence of air, this is the correlation, and where x p in terms of non-dimensional number is given this, and as you can see, given that in the liquid condition, pressure drop equation H T total liquid Holdup can be considered as H T naught total liquid Holdup in absence of air. Therefore, the wet pressure drop equation can be written in this form, where we have substituted total Holdup in presence of gas y total Holdup in absence of gas. So, once we make this simplification, which of course is given in the example, we can, our task become much more easy. So, we need now the gas viscosity. So, gas viscosity is coming into picture here. S T naught we have already calculated in the previous example. So, we do not have to in absence of air, but what we need gas viscosity and the gas velocity superficial. So, these two things we will do it. So, means the gas superficial gas viscosity and gas superficial velocity V g to calculate the wet pressure drop. So, to find the density and viscosity of the gas, density is not given. So, at that temperature we have to find the density of the gas, and this we have done previously in many of the examples. So, that should not be a problem, as you know 1 mole of gas occupies 22.4 decimeter cube. So, rho g is given with the fraction we know of this, and both of them are having molecular weight 28. So, and you know the 1400 degrees 1673 degree Kelvin, your density of the gas comes about 0.2 kg per meter cube at 1400 degrees Celsius. Then rho g is obtained, what we need the gas viscosity. Now, the Sutherland formula is actually this for the gases. So, using this formula, A, V, these are the constant, and where C is the Sutherland constant, and for these particular gases we can get these values from the books of those constant, and once we substitute into this equation. So, for CO C equal to 118, T naught in Rankine, similarly for nitrogen is 111, 140 that Rankine, then the mu naught the viscosity at that temperature is given. So, then we can calculate for the given temperature what would be the viscosity. So, 0.4 is the CO fraction, 0.6 is the nitrogen fraction, and based on these values which are given above and putting into this formula, and we are constant, these are the temperatures. If we you get viscosity of the gas is about 0.0544 centipoise, and that is also given. Those who do not know about the Sutherland formula, they can directly take this value 5.44 into 10 to the power minus 5 Pascal per second. So, but this is quite easy. If you are having a quite a lot variation and you do not know, you can easily calculate the viscosity of the gases using this Sutherland formula, which is quite reliable and getting the values at higher temperature. So, now you got the mu g, you got the rho g, you still need superficial gas velocity for that. So, for superficial gas velocity, you already know the blast volume, which is about 7,000 meter cube per minute. So, in meter cube per second, it would be this. Now, the average diameter of valley and Bosch region is given, which is about 12 meter. So, using that we can get the area of the valley region. So, that comes around 113 meter square. So, if we divide this our blast volume with this blast area, we can get the superficial gas velocity, which comes around 1 meter per second. So, now we come back to the pressure drop equation in liquid flow condition. K1 is already given to us, K2 is given to us, rho g we have calculated, mu g we have calculated, V g we have calculated. What we need now, we have to calculate all these, all other things are given to us. So, taking this one as x1 or kappa 1 and this quantity as kappa 2, we can calculate separately, and of course, the dE which is coming here, which as we have defined before. So, in D what we have done here, again we have assumed the total hold up which was there in the equation in presence of gas. We have substituted that total hold up with in absence of gas. So, St naught, and this is given and quite reasonable that for pressure drop equation in liquid or metal flow we can use this for simplification. So, same thing we have done here, and which is nothing this, and once we use those and dl of course actually is given. So, we directly substitute, as you know the dl is given here. Yes, effective diameter of liquid drop may be taken as 2 millimeter. So, all the parameters are known here now. The x1 is this. So, 190 1 minus 0.43 plus St naught is 0.0267, and dE with that we put it. So, it comes and use all other quantities or velocity and other thing, viscosity, kappa 1 is 19.3. Similarly, kappa 2 is your this, where K2 is 1.7, 0.43, 0.026, rho g, V g squares and d. So, this is all your, so rho g V g square d L S T naught. So, this comes into that. So, kappa 2 you get 654. So, once you know, by putting this kappa 1 kappa 2 here and this quantity over here, you get the pressure drop, which is about this Newton per meter cube. So, now once we got the pressure drop, we can easily calculate our x p. So, x p is nothing delta p w pressure drop divided by rho L g and multiplied with the capillary function and interfacial force inverse of it. So, we have calculated these values. So, we are just simply substituting those and that gives us x p 0.552. And now, this x p we can put in the total liquid Holdup equation, which is nothing, as we have seen, the total liquid Holdup in presence of air is equal to total liquid Holdup in absence of air plus this term. Now, x p we have calculated, total Holdup in absence of gas we already know from previous example. So, once we put these quantities all together, we get the total Holdup 0.0322. So, you can see there is a substantial increment in the total Holdup in presence of gas than in absence of gas, which means it will further reduce your voidage or permeability of the bed in the blast furnace, and further it will affect the operation of the blast furnace. And remember, this just we have done based on the metal flow. We have not taken into consideration the select flow. If we take consideration of the select flow, which is more in volume, this could be much higher, and that certainly is going to affect the voidage in the lower part of the blast furnace, and that is going to affect finally a big the performance of the blast furnace, and that is why these liquid Holdup are important to understand the correct aerodynamics of the blast furnace or the gas velocity. So, one can calculate in a proper way the heat and mass transfer which are occurring in the blast furnace.